Hello, today we will see the simulation of Thevenin's Theorem in DC circuit. So our objective is to perform the experiment and verify the Thevenin's Theorem in DC circuit. So at first here we will see the Thevenin's Theorem, which states that any linear circuit containing one or several voltage sources and resistance can be replaced by just one single voltage source in series with equivalent resistance connected across the load. So if this uh, linear circuit contains several voltage sources and resistance along with the load resistance in parallel, then this can be replaced. This can be shown by this circuit where Vs is the Rs is the equivalent resistance of the circuit, and RL is the load resistance connected with these. So here this is our circuit where V1 is equals to 12 volt DC, R1 is 1 kilo ohms, R2 is 1 kilo ohms, and R3 is 1 kilo ohms, and RL is equals to 1 kilo ohms. So here, if as we are doing the simulation, so the apparatus that is required is we have to write the name of the simulation software over here, and if we are going to perform it in the physically in the laboratory, so then we have to require this table where the serial number, name of the apparatus, quantity of the apparatus used, and range and rating of the apparatus, maker's name of the apparatus, and maker's number is also available on the apparatus. So we have to note it down over here, whatever the apparatus is required, like Thevenin strainer kit, voltmeter, ammeter, if any resistance or anything is required, resistor is used, then we have to note it down over here. So first of all, we have to find out, as per these steps, we have to find out the load resistance from here. Here it is mentioned as RL, so it is load resistance. If it is not mentioned and directly in as RL or load resistance something, then as per the question available, so we have to find out that through which resistance we have to find out the current and the voltage across the resistance. That particular resistance will be marked as load resistance. So as it is clearly mentioned for here in this case that it is RL is 1 kilo ohms, so we have to first of all we have to remove this load resistance from here, and we have to find out the open circuit voltage, which is known as Thevenin's voltage. So here the load resistance is removed, and we have to find out the voltage here. So in practical case we have to attach the voltmeter over here, and for here, as we are performing the theoretical calculation, so we will calculate over here, and when I will perform it in the simulation software, then I will show the steps. And here we have to calculate the voltage. So as this is an open circuit, so no current will be flow. We can consider that the current will not flow through the R2. So the voltage, whatever the voltage will be available over here. In practical case, the negligible amount of leakage current will flow through this R2, but ideally we can consider that R2 will not carry any current. So whatever the voltage will be available at this terminal, so that particular voltage will be the voltage across this R3. Okay, so if we are going to find out the voltage across the R3, so we can find out in many ways. I will show you here the one way, that is the R3, IR3. The current through the R3 is equals to V1 by R1 plus R3. So okay, so here what I'm doing is R1 and R3 I'm considering, and R2 is neglected because no current will flow through the R2. So these R1 and R3 are in series, which are in parallel with the V1. So V1 by R1 plus R3, so it becomes 12 by 1 plus 1 kilo ohms. In the denominator side there is kilo ohms, and so if I divide this 12 by 2, so 6 milliampere will come here, volt by kilo ohms. So this result will come in milliampere. Okay, So now we know that the current through the R3. So if we just multiply IR3 into R3, that means I into R, then we will get the voltage across this R3. That is what I have done. That VOC, that is open circuit voltage across these at this terminal, and which is same as the voltage across the R3. This is also known as the Thevenin's voltage. So IR3 into R3. IR3 value is 6 milliampere, which I converted in amps. So 0.006 into 1000. R3 is 1 kilo ohms, that is converted in ohms. So 1000, that is 6 volt. Okay. And here if I use the voltage divider rule, then also the open circuit voltage or Thevenin's voltage is equals to the V1. Okay, V1 into R3. Whatever the voltage we have to find out across any resistance, that would go to the numerator section, and in the denominator section the summation of the R1 and R3 should be here. So 12 into 1 by 1 plus 1, so that is also become 6 volt. Okay, so we can apply any of that rule. And in the second step we have to find out the equivalent resistance. Okay, so whenever the equivalent resistance needs to be found out, at that time the load resistance needs to be remain or removed, and the voltage source, whatever the sources are available, here only a voltage source is available, so the voltage source is replaced with its internal impedance, that is internal impedance is 0. So I have just short circuited over here, and I have to find out the equivalent resistance looking from the load resistance side, which is already removed. So if we look from this side, then R1 and R3 are in parallel, and which are connected in series with the R2. Okay, so in this step I would like to mention that whenever the equivalent resistance needs to be found out, at that time we have to look from the load resistance side, which was connected here. We have to look from this side, and we have to calculate we have to start our calculation from the opposite side, like what I told, that is R1 and R3 are in parallel, and these parallel circuit is connected in series with R2. R1 and R3 are in parallel, and this equivalent circuit is connected with R2 in series. Okay, so R1 and R3 are in parallel, which I mentioned over here, and R2 is in series. So after calculation it comes 1.5 kilo ohms, and after that in the last step we have to make a equivalent circuit like this. Okay, so here VTH, that is open circuit voltage, which came like 6 volt. Okay, 6 volt. I have to connect the equivalent resistance like this RS. Okay, so this has become RTH or R equivalent, that is 1.5 kilo ohms, and the load resistance should be connected in series with these things. So RL load resistance was mentioned over here as 1 kilo ohm, so I have connected these things, and now you can see that this was a little bit complicated circuit from where we were asked to find out the current through the RL and the voltage across the RL. So now this is become a equivalent circuit, and which is quite easier to calculate the IRL and VRL. Okay, so VRL is equals to VL, and which is equals to the VTH into RTH by RTH plus RL. Okay, so using the voltage divider rule, we can find out the voltage across the RL, that is VRL, which is mentioned over here, and VTH, as VTH was 6 and RTH okay, this should be RL, so RL divided by RL plus RTH. Okay, so this becomes 2.36 volt, and this is the voltage across the RL, and IRL, that is current through the RL, become the VTH by RTH plus RL, that is 6 by this, and this becomes 2.4 milliampere. There the 1000 is multiplied to convert the kilo ohms, these kilo ohms into the ohms. Okay, so we have found out the IRL, current through the RL, and power loss through the RL is I square RL into RL, or we can also calculate it by using this formula, VRL into IRL. Okay, or by using the V square RL into RL. Okay, we can use this formula, and after using this formula it becomes 5.57 milliwatt in theoretical calculation. Okay, so whatever the values I had found out, these values are noted over here. Okay, this was the value of R1, R2, R3, RL and V1, whatever it is available in our question. So it is already noted down, and the calculated values are noted over here. It is marked in this column as theoretical value. So whatever the theoretical values I got from this calculation, so I just put these values over here, and this is the measured values. If you perform the experiment in the laboratory in the physical kits, or then you have to take the readings by using the multimeters or by using the voltmeter, ammeter and the ohm meter. So here I just made the 3 rows for each notation. Okay, just because of to take the readings 3 times to avoid the errors, and as I'm going to perform this in the simulation software, so I have noted it once only. Okay, so now I will and this is a simulation result you can see from here. Now I will go to the simulation section. Okay, so here the same thing is already designed, like from the place to components you can search like 1 kilo ohms in 1k. In the group, basic group, you can find 1 kilo ohms. Okay, if you go specifically to the resistance section, then if you write here 1 kilo ohms, so you will get it from here. We have to place these components like this. Okay, as we need 1 kilo ohms 3 times, so you can just click on it, then copy and paste like this. If you paste here, and if you want to rotate this like this way, in vertical way, then you can click on here, and then okay, just first copy, and then at the time of placement you can click Ctrl R to rotate it. Okay, and to connect the components, then you have to click on simply like this, then click and just connect this like this way. So, and you will get the voltage source also from this place to components, then under the basic source group, then you will get the DC voltage from this section. In the power section you will get it. Okay, in the DC power you will get it. If you want to change the voltage, then you have to click on this section, and under the value tab you can change the voltage like 6 volt. Okay, like this way you will be able to change these values and connect simply like this way. These are the things I took from here. If you just take the multimeter, then this type of symbol, this type of tools will come. So after the connection of the circuit, if I just run from here, then you will be able to see that the current through the R4, that is RL load resistance, is 2.4 milliampere. You can see from here also 2.4 milliampere was the current flowing through the RL after the summarization of this circuit. And if I perform the same thing in this circuit also, the same amount of current will flow through the RL, which I'm getting from this circuit. And step by step the analysis is done to find out the Thevenin's voltage. The load resistance is removed from here, from these terminals. The load resistance is removed and the open circuit voltage is measured, which has become 5.99 volt, which is quite closer to the 6 volt, which I had also figured out from these steps. This 6 volt I had find out from by using the voltage divider rule and the basic mesh analysis. So here I had removed the load resistance and found the voltage over here as 6 volt. Okay. See, one thing I would like to say that you will see that the 5.999 volt is available over here just because of this R6. As I had already told that the leakage current will flow through the R6, that is happening. So our minimum amount of voltage drop, that is 0.001 volt voltage drop has occurred over here. So due to that, it is showing that the 5.999 volt. For our calculation, we had ignored that one, and in the practical case, we will also get some voltage deviations from the 6 volt level. So just because of the current flowing through the R3, here I would like to mention that you have to note this point, as I am doing the experiment in the same page, so the notation of the resistance has changed. Here I would like to say that R1 is equals to the R5 and that is equals to the R8. These are the same. You can just note that the point of the attachment of these resistance are in the same place with the main circuit. Okay, just to show in a single page that, so that I have done like this way. So R5 is equals to 1 kilo ohms, which is equals to the R1, which are placed at the same point. In the similarly, I would like to say that the R2 and R6 are placed in the same point, and R3 and R7 are placed in the same section. Okay, so the open circuit voltage is 5.999 volt. Okay, and after that, if we just go for the equivalent resistance to find out the equivalent resistance from this circuit, we have to replace the sources with their internal impedance. Here the voltage source is available, so internal impedance is 0, so I have just short circuited on here. And if any current source was available over here, then in that case we have to replace the current source with its internal impedance, that is infinite. So in that case we have to open circuit this section. But in our case, it is a voltage source, so the short circuit is done over here. And from the also the load resistance is removed from this section, and the equivalent resistance is measured by using the multimeter. See, it is showing 1.5 kilo ohms. This is also same as our same with the theoretical calculation, 1.5 kilo ohms. And then finally this open circuit voltage, that is Thevenin's voltage, in series with the equivalent resistance of this circuit, that is 1.5 kilo ohms. So 1.5 kilo ohms is attached over here, and the load resistance which was available here with the notation of R4, that is also attached over here. So the current flowing through the load resistance is 2.4 milliampere, and the voltage drop is across this RL is 2.4 volt, which is similar to the main circuit. This is the circuit of Thevenin's equivalent circuit, and the power loss is 5.76 milliwatt. if I just place this wattmeter over here, okay, so I place the wattmeter over here. In that case also you will see that the same amount of power loss has occurred over here in the main circuit, and in the Thevenin's equivalent circuit the same amount of voltage, current and power loss has occurred over here. Okay, so this is the Thevenin's equivalent circuit experiment which I had done in the simulation software. If you want to find out the voltage or current in this section in using this multimeter, then you have to just choose the voltage or current like this way, as in there are no voltage sources available, so no sources is available in there, so the current and voltage are not showing over here. Okay, and we can find out the equivalent resistance from here. So that you have to click here on the ohm symbol. So at the end we can say that the precautions should be taken care of by the student while performing in the physical trainer kit. So in that case the loose contact should be avoided and the proper range of instrument should be used while performing the experiment, and the tolerance value should be of the component should be noted, because according to the tolerance value it will the calculation will be changed, and the gross error should be avoided at the time of measurement, like parallax error for the analog type instruments, and for the digital type instruments the values should be noted properly. So from this experiment you saw that how can we perform the Thevenin's theorem, and how can we verify the Thevenin's theorem using this simulation software. Once again I would like to say that this was our main circuit in which the voltage, current and power has measured, and after that according to the Thevenin's theorem the step-by-step operation has been done. In this section we had tried to find out the Thevenin's voltage, that is open circuit voltage, after removing the load resistance, and after that the Thevenin's resistance is found by using the steps as mentioned, like the sources needs to be removed and replaced with its internal impedance. For voltage sources the internal impedance is 0, and for current sources internal impedance is infinite. So here voltage source is available, so I short circuited with here at this terminal, and equivalent resistance as measured from this load resistance section after removing the load resistance. And finally the Thevenin's equivalent voltage that is found over here, this is VTH, okay, and the equivalent resistance in series with the Thevenin's voltage, and the load resistance which was mentioned in our circuit that is placed over here, and the voltage, current and power loss as measured once again on the load resistance. So you can see and we can conclude it that the voltage, current and the power loss are the same in the quantity in the actual circuit as well as in the Thevenin's equivalent circuit. Okay, thank you. This was for today session. While performing the experiment you have to connect the ground compulsory. This is compulsory to connect, and you will get it from the place to components, then sources, then you will get this ground like this, and you have to connect it like this way, and you will also get it from here. In the description section you will find this file and the simulation file also, and you will be able to change the values of the circuit and you will be able to perform the experiment in your computer. Keep watching and stay tuned with this channel to get the next video on the other lab experiment. Thank you.